Hello everyone, welcome to X598 Introduction to Silvaco. I'm Ashley Jian and I'm the PhD student in Professor at Maddie's group. Today we're going to talk about how to launch the Silvaco, the basic function of Silvaco, and how to load the example provided by the Silvaco, how to modify it, which is very important for your future project. Let's get started. So you can run the simulation software either from the computer in the Can lab on campus, or you can run it from your own computer. So first, if you're gonna go to campus and run this software, the Silvaco is available in the Can software list. So you just go there, launch the Silvaco, and that's it. If you want to do the remote control, especially first we're gonna we have to install the software called VMware Horizon Client. This is necessary for the all remote control. And also, if you are studying remotely outside of the US or you find your internet slow and unreliable, I would also recommend you download the Umich VPN or the MLAN. So let me show you how to search these three softwares. The first is called VMware. So basically, I just searched this VMware image, and you can see the first one is that. We go down, and you can see select install the VMware Horizon client. It is available for both Windows and MacBook. Today I'm gonna do the demo using my MacBook, but it is very similar between Windows and MacBook because our remote control is to control a Windows system. Yeah, and you click here is very straightforward. The second one is the VPN provided by the University of Michigan. So basically, you can just search image VPN. Oh, sorry. Yeah, the first one, getting started with VPN. A lot of systems are supported. You can just go to the Windows and click the student, and then you will download and install the VPN, just following the instruction. It is very simple as well. The third thing is called MLAN. It is recommended by my friends right now in China, and she noticed that if she runs this software, her Silvaco simulation is really, really fast, and that helps. So it is also provided by University of Michigan. Yeah, you can see here. Studying remotely from China, and it can give you more reliable, high-speed access to the Can lab. See, yeah. So first, please download all the software that is needed. Yeah, and then we're gonna launch the Silvaco. So the basic step is first we run the VPN if necessary, and then the next step is we run the software called VMware Horizon Client, and we're gonna log in using our unique name and password, and we also need to pass the two-factor authentication. If you have not registered for that, please register now. And also, we're gonna go to the Can lab remotely. So let's now do it. It takes a minute. So this is that software. Yeah, so first you can see here, it asks for the username, which is our unique name. And the password is also what we use to log into the Open Access website. Yeah, first we click login, and you can see another window is pop up to ask you for the dual two-factor. So I'm gonna use the first one, dual push, to send a push to my cell phone. Yeah, so then we just select this Can Labs 2020. If you have some more specifics requirement, for example, 16 gigabytes RAM or some graphics thing, you can also select the following things. For the Silvaco, it is okay, we select the first one. And then we go into this desktop. It takes a second. Oh, so there's another thing I want to mention is for this VMware Horizon client, this software will be closed every 10 hours. So like if you open this software, but like you have some unsaved data or results after 10 hours, everything is gone. Unless that when it is closed, that you immediately open it within 10 minutes after it is closed. So it is like now we are starting this software and then kind of we need to calculate like what is like after 10 hours, what is that time? And then we need to be pretty sure we are in front of our computer and open our software. Why I'm mentioning this is like, for example, in the future, if you are gonna run some more complicated simulations, which may last for like more than 10 hours or like even several days, what you need to do is for the remote control, you have to be sure that you calculate what is the next 10 hours. And we need to open this software immediately. Otherwise, like everything is gone. Because if you do not open your software within 10 minutes after it is closed, the remote control computer will also be shut down. That means like everything unsaved is gone and you have to rerun your simulation. So that is just a kind reminder if you want to run more complicated simulations in the future. Yeah, you can see like right after you enter the Windows system here, this can software pump up automatically. So first we search the apps, like here it is Silvaco. See, it is shown here, and then we click launch. When the status is shown as ready, we can click launch again. So then this window is shown here. We're gonna use the deck build to do all the simulation to like kind of launch the Silvaco. But you can also see like we have a lot of tool list shown here. The deck build is like a framework for calling and like organizing tools. So for example, if I click here, it is the window you can see shown here. I'm not sure if you can see clearly. What I want to just to quickly mention that you can see a lot of tools is also now embedded in the deck build. It is the deck build is the organized tool to like call every other tools. So you can see like the TonyPlot, which is used to plot all the plots, and like TonyPlot 3D, and like the dev edit, which is to create the structure. Yeah. So first I would like to do is like we're gonna do many projects for 598. So first I would like to create a folder, for example, in the desktop, and also like don't worry if you create anything here, put that in the desktop, they will not be like deleted after you turn off this computer. So like you can also see this folder, see many data next time. So as long as you put it in the correct place. So what I recommend is we just put everything now in the desktop, in the remote control computer. So for example, I just put, yeah. And then we go back to this deck build. First, how to let the software know that we want to save all the data to that folder I just created. I would just put like first we save as, we go to that folder. So how to go there? You will first click this My Computer, and then you click the disk N. Before the disk N, you should be able to see your unique name there. And you click, then you click the windat.v2, and then the desktop. You can see 598 project. So I go there, I just give a random file name, and then you can see we go back to this folder, it is saved there. So the .in file is the file we're gonna run. So like it's the file we use to run the Silvaco simulation. So this is just the code file. And what we want to do is like, first we load the examples and you will see like more clearly how that .in file work. And I want to run the power device example. Oh, it is here, power. Okay, I'll do this. Wide bandgap gallium oxide MOSFET. And I click this example. You can see the example explanation and all the output figure are all shown here. But it is like just for view and you cannot do any modification. So what you want to do is you click this and then you click load. So all the output file, all the in file, all the settings are now loaded into the folder we just created. See, like this is the in file. So like every time you want to run the simulation, we need to open this .in file. And we also have some output file. And the PNG file is like to give you the result of the structure of the IV-CV curve, something like that. Yeah, so see, the .in file now it is loaded into our deck build window. You can see this is the power example 17.in. I can click run now, so you can select now this simulation is running. It takes a couple of minutes, so I can first explain the codes, and then we will see, we understand more. I think I'm able to, yes, I'm able to open another window when this codes are running. Yeah. So first we go to the outlets. What outlets does is to help us create the device structure, apply the physics model, and also apply the electric field, the bias voltage on our device to test our device performance. So first we need to go to the outlets. Yeah. And the second is the mesh. You can see here, the mesh width equal to 1E3. So first we need to know that the default unit is the default unit in Silvaco is the micron. And we are now building a 2D device, which means like one is x-axis, one is x-axis, one is y-axis, but we also have a z-axis if you want to do like a 3D device, or you want like your device somehow give you more decent values, or like the current, you want to get more current. Yeah, so here the width equal to 1E3 means we assign the device width in the z direction, and the default unit is micron, so which means in z direction our device is 1000 micron. Yeah. And the second is to define the real mesh for the x and y axis. First, what is the mesh? The mesh is like you first have your device and you want to make your device into small cubic. And that mesh is important because for the area with smaller mesh, that means we have more calculations there. We are very interested in that, like the active region of the device, and also like for the interface between two material, we also prefer smaller mesh right there, because a lot of perturbation, a lot of changes might happen there. So here the mesh is also very complicated thing. If you want to study more, there's a manual especially on this mesh. And sometimes if you give the device wrong mesh, or I shouldn't say wrong mesh, like not proper mesh, you can see like your result is changed significantly, and that result even is not meaningful. So what the basic idea is what I just mentioned, that you give the device interface a smaller mesh, you give the device active region smaller mesh, and also you think like in which area you have a more perturbation, you have more change, a more abrupt change in that area, you give smaller mesh. There is also another important thing I need to mention is for the mesh, you can see we give is x-axis, like from -2 micron to 22 micron, and also y-axis, we give -0.02 micron to 0.5 micron. So which means like for our 2D device, we give a mesh which is a square, right? But sometimes your device cannot be a square. Like for example, FinFET device, some other device. So but if you do not fill the mesh with a square device, you're gonna get the error when you run the code. So what I typically do is to suggest like you can give the empty area without like the device is not in that area, the empty area, you give the air. You can assign that area, the air or the silicon nitride as passivation. So just to make sure to fill all the mesh you're assigning here, it is very important. Yeah, so now let's understand like what this code means. X.m means we are now determining the axis mesh, and L equal to -2 means that that is the position of the mesh, and then S equal to 0.4 is the spacing between meshing point. So like that means like from -2 micron to 0 micron, the spacing between two mesh grid is 0.4 micron. And you can see we also have like 0.1 micron. So I believe in this area, it is either the active region or the interface between two material. So the same thing, we define the y-axis mesh from -0.02 to 0.5. And also the spacing between two mesh points. After we define the mesh, we have not created our device structure yet. So here, the region, this code, this command means we're gonna create our device structure. So first is the region, and then region number 1, we give the material aluminum oxide, and then we are here having y dot max is 0.0. So actually the region we are building here is also like a rectangular region. We are supposed to give x dot min equal to blah blah x dot max and y dot min. But here, why does this code only show the y dot max? That means if in default, if we do not give x dot min, x dot max, we are giving this as x dot min, like -2 micron, and this as x dot max, which is 22 micron, and y dot min is -0.02. So that although we are only giving the y dot max right here, but we are actually creating the rectangle, which is like the x-axis is the x coordinate is from -2 to 22. The y coordinate is from -0.02 to y dot max is 0. So this is that rectangle. And also the same thing applied on the region number 2, region number 3. So for all the missing coordinates, is just we use the coordinates from here as the x dot min, x dot max. And so this is to create the device structure. Apart from the material, and also we need to give the electrode, like for example, the source, the gate, and drain. So you can see here for the source, gate, and drain, we have our 4 coordinates are all shown here. For the electrode source, we have like x dot min is -2 to 0, y is 0, 0. You might wonder that how come like our two coordinates here are equal to each other. That means that our source electrode doesn't have any thickness, right? So like it only have the x coordinate and y is the 0. That means it's like a line without thickness, and it is allowed in Silvaco. So the same thing you can see here for the gate. The y coordinates right here are also the same. The drain here is also the same. The only thing that is changing is the x. Yeah, so after the electrode, we are also assigning the doping. The doping is, so the doping should be defined after the region, because you can see for the doping, we first assign the region number. So like for the region 2, 2, 3, oh, I think the simulation just now has done. So yeah, you can see this is the simulation we are running, and the output now is shown automatically, like the basic drain current versus gate voltage curve shown here. Oh, sorry. Yeah, and the TonyPlot is used to plot the curves. It's like we have the like a perfect IDVD curve, and one is simulation, one is experiment, and they are fitting each other, matching each other. And we also have like, yeah, so like our device structure can also be shown here. What I just said now, like for the source, drain, and gate, they do not have any thickness. It's just one line. So you can see now it is shown here without any thickness. Yeah, here it is the doping, the net doping shown here. It is what I just mentioned. I think it's right here. You can see like we assign the region 2, the doping profile is uniform, and doping type is N-type, concentration is 1.1, 10 to the times power of A17. And we can also assign the Gaussian, the uniform. So for doping, we first need to know that we assign a region, we assign the doping profile, we assign the doping type, and also the doping concentration, and that's it. If you do not assign any doping for one region, that means that region is like intrinsic. Yeah. So after doping, we have this material. So for the material property, because gallium oxide is a very new material, and now Silvaco has not added that material to the user material. So we need to kind of give the Silvaco additional material property, like here, like the electron affinity, the band gap, NC/NV permittivity, like this. Yeah, and also next we're gonna give the models like we're gonna apply the models on our device structure. So like sometimes you can see, oh, I really want to see the Shockley rate hall. I really want to see the Fermi Dirac, and here you can see we are gonna study the lattice temperature, like the thermal conductivity of the material. So we give the physical model right here. And for the models, there is also the manual, and you can see like a lot of physical models right here. So it is very important that you give the correct model to study, like sometimes you wanna study the thermodynamics, sometimes you wanna study the electrical properties. So it really matters that which model you are giving. So for example, I now study the thermal thing, and apart from the model, I also give some kind of the thermal conduction property, the parameters right here. I'll skip this part because it's very detailed thing. So after the model, we're gonna give the method. The method is like which numerical method you're gonna use. So what I do not recommend you to change this limit right here. It is like the current limit to kind of control the resolution. this is called the trap. So that means like after 10 times of the iteration, if you still do not get your solution, that means your numerical solver will break the current loop and go to the second bias. So for this trap, you can kind of make it larger if you are dealing with the wide bandgap material, because it is harder to kind of go into the comes into conversion. So I would recommend that you make it a little bit larger. Like sometimes you try 20 or even 50. If it doesn't work, yeah. And then we're gonna determine like what is the output right here. So here we're gonna show the conduction band and valence band. So after all these things above, we have done like our device, the how to generate and create our device structure, which was shown just now in that TonyPlot. And after that, the following thing is just to apply the voltage, some perturbation on our device. For example, you can see here we're gonna put like the gate voltage equal to 0.1 watt, and then make it ramp up until like 4 watt, and then we give the drain voltage from the 0.001 to the final like 25. You might wonder like why we're gonna going through this from the small thing to the final 4. Why we cannot just go directly to let the gate voltage equal to 4. Because like sometimes we see like the simulation is very hard to get converged from the beginning, and you can see like our step is larger, like it's very small at the beginning, and then when it is go higher, you can see the step is larger and larger, like from 2 to 25 the step is 1. So that means the drain voltage will be going from 2 and then 3, 4, 5 until 25. So I would also recommend that when you are doing simulation or you are modifying the codes in the future, please start from the small step from 0 to 0.0 something, and then go to larger. And you will also find that you will have a very, very smooth curve from the beginning. And then kind of when it goes to the larger voltage, you will see like for sometimes like for the ID/VD curve, you're gonna saturate or something. So it doesn't matter too much if your step is larger. But it is also like up to your kind of your requirement on the simulation. If you really want the step smaller for the larger voltage, it is okay also that you kind of do like the step equal to 0.1 for the drain voltage above 2 watt. It is totally fine. Yeah. Yeah, the same thing for the following, just to give some voltage and to solve the result. Yeah, so like how to solve the result is first we have a command here. It's like we're gonna generate a file called this power example 17.2. And then we solve all of these things. We get the current under this bias, and then we log off. Means we stop saving this current numbers, voltage numbers into that log file, and then we will have that log file. So if you look at that, you can see like, yes, our log file like power example 17.2 is saved here. Yeah. All these codes are just run the different bias. And then after this, we also we have this TonyPlot command. Is just to plot what you, the data you just solved. So the first, so for the output file, we have 2 types. One is, you can see here, is the .str. The other is the .lor, the .log. The str is the structure file, which we have seen just now, like the structure of the device, maybe your doping, like everything. So that is the structure file. And the .log file is the file to save your like your IV, CV curve. It's something like that. The dot data file is the same as the .log file. You might also see that we have another thing called .set file. It is like how you plot your file. So even though you do not have this file, you can still output, like view your structure file. This setting file is just to say, oh, I want to have a title, I want to have a grid there automatically. So that can be done in using this setting file. So for example, you can see now I'm not running that code, but I can still open our output file. How to do that? You can see here we have a TonyPlot embedded in our deck build already. And I click this. Yeah, excuse me. Yeah, so I go to the folder just now. So first, let's take a look at the structure file. It's here, .structure. Well, it is very simple. I just drag this file into the TonyPlot. If the structure is very kind of complicated, you'll see like it takes even up to 1 minute to show this structure. But it seems like this example is very simple, so we can view this structure immediately. So you can see that we just now we created the aluminum oxide region, we created gamma oxide region, the 2 gamma oxide region. This is the MOSFET. So this part is just the substrate, the N plus substrate, and this part is the drift region. I will skip like the explanation of the device because this is just a random example I pick up. We right click on our structure and we click display. You can see we have a mesh, edges, regions, contours, vectors all shown here, and even junctions, electrodes. So like if I select the electrode and apply, you can see our gate, source, and drain. And also like, yeah, we can take a look at our device. So you can see like under the gate, the mesh is a little bit smaller than the other area because we're really curious about how this device, what is the device behaviors, like the channel behaviors right here in the active region. Yeah. How to turn off the mesh is just to unselect this. And not only this, but also the contour is very powerful thing. It's like for example, you first select a contour and you click define here, you click contour, you see we have a lot of things can be shown here, and these things are all defined in the output just now. Let me see. I'm sorry. Oh yeah, it's here. The conduction band, the valence band. If you do not, and also something, if even though you do not define here, they can also be shown automatically because they are viewed as the basic output. And also you can also add like the electron mobility, electron velocity, many things here, and you will view your structure here. So for example, I would like to see like right now, because our structure is saved before applying the voltage, so it is not meaningful that we take a look at the electric field. But in the future, if you want to do this for your project, the electric field is a very powerful thing that you kind of analyze your device. So what I want to show here, maybe it's just the basic net doping. Yeah. So if you still remember, like just now we have the different doping, like the uniform doping in this region, and also the 2 Gaussian doping for the N plus region under the source and drain. So you can see the doping is right here. There's another powerful tool I want to introduce is the cut line. So for example, like we can see now that this region, the orange region, the doping is somehow around like 10 to the 13 to 10 to the 16, but we don't know like what is the exact value. So I would suggest we do a cut line. We have like the vertical, horizontal, and 45-degree. Cut line, we can also assign the XY coordinates to get a very perfect uh, specific cut line. So right here, I just want to kind of do a cut line. I select the vertical cut line and we drag a line from the gate to the substrate. And you can see your cut line here. This empty part is because I draw this from the air. So you can see our, yeah. So our doping is like 10 to the 17 and then down to the 10 to the 16. It sounds like this. Yeah. And let me see. We also have a ruler here that you can measure the device dimension. But I would say like if you can understand like what is shown here for the region and everything, you uh, I feel like you get a number from here which is more accurate than you use the ruler in the TonyPlot. Yeah, so this is for the structure file. I delete this. And then we can also take a look at, for example, the data file. I drag this data file here. Yeah, so this is the drain current versus the gate voltage. So it is shown here automatically. But sometimes the file is not shown here automatically. For example, maybe, let me see. Okay, so for example here, it is the IDVD curve. But sometimes maybe it will show you nothing like this. So what we need to do is we right click and then click display. We need to assign that what is used, what is shown for the axis. So here we just say drain voltage. For the y-axis, we say the drain current. So we can just put these two here, and then the curve is shown automatically. Yeah, I think this is the basic Silvaco. You can, let me see. Yeah, so if you are also curious about the setting, I can just show. I'm not sure what is shown here for the setting. Yeah, so you see it is just like the graph with the sequence mark, the function, just some basic things. So like even though just now we were not using the dot setting, which was shown here for the for this, we can still view our view our results. It is totally fine. The settings just somehow make your plot more beautiful like that. Yeah, so I would say like when you are debugging or you are modifying your codes, it is totally fine that your setting cannot work for your current code. So you just ignore that setting and do your own plot. Oh, there's one thing I forgot to mention is the how to save your data. Yeah, so like here for the structure, how to save. First, you can drag to your area of interest, and then you go to the file, you save as. You can save as the PNG file, and then you give a file name. And the same thing, the similar thing for the data file. Let me delete this file. For example, here, if you save here, you save as a PNG, which is okay for like for the project, or like you are satisfied already with the plot here. But if you want to replot it or you want to extract the slope very accurately, you can also do is to export the data. So it is like the TonyPlot user data right here. And then we give a file name extension. We select the displayed only, because if you do not select all the other data, so for example, the gate voltage, everything is also saved in that file. And then you give the file name, you select your folder, you can also export your data, and you can plot that again using either the spreadsheet or the MATLAB to kind of further analyze your data. Yeah, I think that's it. Let me see. Oh yeah, so there's another thing I want to mention is so first you can get access to all the examples provided by Silvaco. Yeah, this is like there are so many examples. If you don't quite understand the example, so like although here we have the explanation for the example, but if you feel like this window is so small, I'm not comfortable with it, I would say like you just go to Google and kind of say Silvaco example, and all the examples shown just now are shown here. So for example, what I picked up just now is the power device, the wide bandgap gallium oxide MOSFET. I click it. See, the explanation is also shown here in the website. And even the references are shown here. We have the output result here as the picture file. And we also have the input deck, the .in file shown here. Although we cannot run the codes here in the website, but it just gives you like a basic idea. Like if you want just to check this code or check this example, it's very easy and straightforward. So if you want to kind of study some examples yourself, I highly recommend that you go to the Silvaco software website and you click several examples and study the code, study this, study the models like this. And in the same time, at the same time, I would also say that there are many manuals which are very important for you as a reference to modify the code. So how to do that? So you can see here we are now in this folder. We go back and we have a library folder here. You see we have the atlas, and you double click and you go inside. You click the dot, and you will see your user file here. And when you click it, it is like a several hundred pages file. And all the physical models, all the like how to do the mesh and everything is shown here. It is like a very, very powerful and great manual. I highly recommend you kind of look at it in detail. Yeah. I want to find something very straightforward. It's okay. So for example, if I select, I'm looking at the model thing, like the physical model right here. Like you can see we have a lot of physical models. So maybe in the future you are doing like the breakdown voltage simulation, and you really need to apply this 3.6.4 impact ionization model. Because if you do not do that, the breakdown voltage is definitely not accurate, right? So this is just the basic introduction to Silvaco. I would highly recommend that you take a look at the examples provided by Silvaco and also the manual right there. You don't need to go through the manual like that, several hundred manual yourself. It's just like you use that as a reference if you are doing the debugging. And everything I just talked about is all put here in the slides, like the outlasting, TonyPlot, dev edit, and deck build. And that example I was explaining, what I was explaining, I also put the annotation right here. So because I put the annotation here, so the line number will be a little bit different from the examples provided by the Silvaco. Oh, and how to show the line number? It is here. So like you go to the view, you show the line numbers. Yeah. And here's like a way how to do the cut line, how to save the plot and extract the data. Yeah, and how to get access to the menu. Yeah, thank you.